GameSide.com. GameSide.com.
Yo, 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 what's up? Time for a lesson on B trees. Configure an always balanced multi-way tree data structure. Here's a node with 5 keys and 6 children. 1, 2, 3, 4, 5. 5 keys in a node with 1, 2, 3, 4, 5, 6 children. What's up with that? A binary tree has at most 2 children per node. A 2-3-4 tree has at most 4 children per node. A B tree lets the programmer configure the number of children per node. A B tree is all about disk storage and making sure one B tree node equals one disk sector. If 4 records and 5 child links fit in one disk sector, configure a B tree with 5 children per node. If 7 records and 8 child links fit in one disk sector, configure a B tree with 8 children per node. B trees are configurable. You can set the number of items and keys in a node to match your disk sector size. B trees. Things you should know. A B tree is always balanced. Leaves are on the same level. If it takes 6 levels to reach one leaf, it takes 6 levels to reach all leaves. Above tree just has 2 levels. A 6-level tree wouldn't fit on this slide. 1, 2 levels to reach that node. 1, 2 levels to reach that node. 1, 2 levels to reach that node. All the leaves are on the same level. This is what we call an order 6 B tree. A non-leaf node has a maximum of 5 items and 6 children. A B tree with a maximum of 7 items and 8 children is called order of 8. 1, 2, 3, 4, 5, 6 children is the maximum a node can have. That's an order 6 B tree. Order is the number of children. Some books and websites differ on this, but most of them say the order of a tree is the maximum number of children a non-leaf node can have. It's important to understand the relationship between the keys and the children. X keys means there will be X plus 1 children. Or, looking at it the other way, Y children means Y minus 1 keys. If I have 1, 2, 3, 4, 5 keys in this node, I have 6 children attached to it. Let's look at some B tree terminology and the terms used to describe B tree. Key 0, key 1, ... key n minus 1. Key 0 is always the smallest value in the node. This is key 0. Key 1, key 2, continue on to key n minus 1. In this node, here's key 0. Here's key 2 in that node. Here's key 1 in that node. Key numbers start at 0 and continue up from there. Nodes are sorted. Key 0 is always the smallest value, and key n minus 1 would be the largest value in the node. This example uses integer keys because they're simple to understand how B trees work. But a key can be anything that supports less than, greater than comparison. A long social security number, a string email address, or object references that provide the key and or comparison methods. That's the object-oriented programming way to do it. Anything can be a key as long as you can compare it for less than and greater than. More terms. 0 child, 1 child, ... to n child. Like the keys, the children are numbered starting from 0. Keys and children are stored in arrays. Here's the 0 child, the 1 child, the 2 child, the 3 child, ... over to the n child. Like the keys, the children are sorted. 0 child keys are less than 1 child keys, and so on. 5 is less than all the keys here, 15, 20, and 25, which is less than this key, 40, and so on down the line. Children are usually stored as integer disk sector numbers. What does that mean? If the node containing 5 is written to disk sector 1, 2, 3, the left child of 10 in the root is 1, 2, 3. B trees are designed for disk storage. If this node is stored in sector 1, 2, 3, this reference Left reference of 10 is set to 1, 2, 3 to tell it which dissector to read. More terms: a 2 node, a 3 node, an n node. A 6 node has 5 keys and 6 children. If you look at this node here, 1, 2, 3, 4, 5 keys. 1, 2, 3, 4, 5, 6 children. That's why this is called a 6 node. A 3 node has 2 keys and 3 children. 1, 2 keys, 1, 2, 3 children. That's a 3 node. It's extremely important that you understand that keys plus 1 equals children. If I have 2 keys in a node, it's 3 children. If I have 5 keys in a node, 6 children. Understand the relationship between the keys and the children. All the keys in the subtree of child 0 are less than key 0. All the keys to the left of 10 are less than 10. All the keys in the subtree of child 1 have keys greater than 0, but less than key 1. Between key 0 and key 1 is this reference right here. These values, 15, 20, and 25, are less than 30, but greater than 10. All the keys in the subtree of child 2 have key values greater than key 1, but less than key 2. This is child 2. It contains a 40. It is greater than 30, but less than 50. All the keys in the subtree of child n have keys greater than the key n minus 1. Key n minus 1 is the value 90. The right child contains values 93 and 95, which are greater than 90. If this were a larger tree with more levels, everything below child 0 would be less than key 0. Anything hung off of this node right here would have to be less than key 0. A B tree is like a BST with fewer levels. Technically, you can convert between a B tree and a BST, but you probably won't. Why not? I could take a balanced B tree like this one here and convert it to a binary tree. It would take far more levels than I have room to show, but I could do it. Why won't I do it? Because B trees are designed for disk storage. Each node takes one disk sector. Each level means a disk sector read. A 5-level tree means 5 disk sector reads. B tree algorithms are designed to minimize the number of levels to limit the number of sector reads required. In other words, B trees are purposely designed to take fewer levels. Binary trees take many levels. B trees take much fewer levels. Since each level of the tree requires a disk read, the fewer the levels, the fewer the disk reads. Let's do a find of 65. Search the B tree structure for the value 65. Less than to the left, greater than to the right. That's all, folks. With the strong link between binary search trees, or BST, searching the B tree is familiar. Start at the root and move down the tree, finding the key or moving down the proper link. The only difference is you have to choose between up to n children instead of 2 children. Once again, if you find the key on the way down, you stop. If you reach a leaf and it's still not found, the key's not in the B tree. If you understand searching a BST, you should understand searching a B tree. It's very similar. We'll scan the root for 65. If the target 65 is less than item 10, it is not, go to the left child. If the target 65 is equal to item 10, it is not, we would return. If item 10 is the last item in the node, once again it is not, we'd go to right, continue the scan to the right. So we'll make several checks on this value, but none of them are true, so we will continue scanning to the right of the root node. Scanning the root for 65, we're just going to go across here. If the target 65 is less than 30 or 50, it is not. I'm scanning down the root, looking for the path to take. None of these are less than, so I'm not going to take that path. I also did not find the target 65, so I'm not going to exit the algorithm. If item 30 or 50 were the last item in the node, I'd go to the right. None of these are true. I'll just continue scanning to the right. You'll scan through as many items as you have to as long as the target 65 is greater than the key. And none of these are larger than 65, so I will keep scanning. Scanning to the right, I find 70. Target 65 is less than item 70. This is a true statement. Let's go to left child. Did you see what happened there? I scanned all the way across this node till I hit a value larger than the one I'm looking for. At that point, I go to the left child down this path. And I'll set the current node to the left child of 70, which is this node right there. Now let's scan the child for 65. We move down the tree to continue the search. We've got to repeat the scan on this node, the current node. If the target 65 is less than item 60, it is not. If the target 65 is equal to item 60, it is not. If 60 was the last item in the node, it is not. None of these are true, so I will continue the scan to the right within the current node. Continue the scan of the current node. If the target 65 is less than the item 65, it is not. If the target 65 is equal to the item 65, that is a true statement. We have scanned this node and we have found what we are looking for. We need to return found. The search is done. The search can stop when what we're looking for, 65, matches what we're looking at in the tree, 65. Let's do a hypothetical. What if we were scanning for the node for 67? What if we were scanning the node for 67? What happens when we look for a key that is not in the B tree? Pick up find from where we just left off. If the target 67 is greater than the last item in the node, that's a true statement. We need to go to the right child of 65. When the search sends you to the right or a left child that is -1 or null, return not found. This is just like every other tree. When you reach the bottom of the tree and you try to go right or left and there's nothing there, the search is unsuccessful. Return not found. Children in a B tree are usually stored as integer dissector numbers. If the node containing 60 and 65 is written to dissector 456, the left child of 70 in the root is 456. B trees are designed for disk storage. I'll store -1 to indicate that there is no child to the left or right of 65. Since disk drives do not have a sector -1, it is often used as a flag to indicate null or no child. A strong understanding of how a B tree find/search works is critical because it's just like with binary search trees and 2, 3, 4 trees. The insert and delete operations always start off doing a find of the target item before the insert/delete. B tree insert. Insert maintains perfect balance. Inserting new items into a B tree is almost trivial when there is free space available in the leaf node. B tree insert is very much like an insert into a 2, 3, 4 tree. The differences occur when it's time to split nodes. What I like about B trees, as the nodes fill up, insert gets a little more complex with each new scenario, but at all times the tree stays in perfect balance. Perfect balance means you passed through exactly the same number of nodes to reach each leaf, 2 in the tree above. Perfect balance says it takes 2 nodes to reach this leaf, 2 nodes to reach this leaf, and 2 nodes to reach that leaf. Insert 25. Start with the easiest insert, into a leaf node with plenty of room. Find the leaf node the item belongs in and place it there. B tree inserts try to go into the leaf node, but there may be exceptions when the leaf splits. Since the target 25 is less than 30, we will go to the left child of 30, moving down the tree looking for the leaf node to place the new item. Continuing with the insert of 25, we have found the leaf node that 25 belongs in. Very important, the new item must be placed in a sorted order. An item smaller than 20 means 20 would shift, so the new item could insert before 20. In this case, 25 is greater than 20. It must be inserted after 20. 25 belongs right there. Completing the insert of 25. Item or key 25 is placed into the leaf node with plenty of room. Easy peasy. All I had to do was put it at the end of this leaf node. But most important, make sure the node remains in sorted order after the insert. 20 and 25 are in sorted order. Let's do a new insert of 43. Start an insert of 43, which is only slightly more difficult than the previous insert. Since the target 43 is not less than 30, stay in the root and go to the right. Continuing the insert of 43, this is the find phase before the actual insert. Since the target 43 is less than 50, we need to go to the left child of 50. Move down the tree looking for the leaf node to place the new item. Continuing the insert of 43, item 43 will be placed in the leaf node. It's important to make sure the node remains in sorted order after the insert. Shift larger items than 43 to the right before the insertion. Shift the new item to the proper position. What? Again, it's important. Just make sure the node remains in sorted order after the insert. The 45 is shifted because it's greater than 43. But the 40 is not shifted. It is less than 43. Open up a spot to place the new node 43, and that's what we've just done right there. Complete the insert of 43. Bee trees try to insert into the leaf. 95% of the time, a great amount of the time, bee trees insert into the leaf. There is an exception when the leaf splits, but most of the time the insert is into the leaf. Just make sure the node remains sorted. The 43 is placed in the correct spot between 40 and 45. This is not hard. You just have to shift the larger items to complete the insert. Let's take it up a notch and insert 40, which is going to go into the node which does not have room for it. This will cause a split of a bee tree leaf node. Insert 40 into an order 5 bee tree. That means there is a max of 4 keys per node. Split when the 5th item or key is added to the node. Since the target 40 is not less than 30, stay in the root and go right. Continuing the insert of 40. Since the target 40 is less than 50, go to the left child of 50. A simple find of the leaf always starts the insert operation. All trees work this way. Find where the item should go. We are in the find phase right now, searching down the tree. Continue the insert of 40. Insert the new key 40 into the full node. Before we split this node, shift the larger key 45 over and place 40 in its proper position into the full node. With a bee tree, we insert the new key first, then split the node. That's because they're on disk drive. With a 234 tree, we split first, then insert the new key. That's because they're in RAM. This is a leaf. Let's step through the leaf split algorithm. We've done the first step. We've inserted the new item into the full node. Do you see why I left a blank spot there? I left an open space in there because I knew we were going to be splitting and I knew we'd need room for a new node. The next step is to create an empty node to the right of the full one. The new empty node is needed because an order 5 B tree can contain at most 4 keys, and the node to the left has 5 keys after the insert of 40. Cannot have a node with 5 keys in it. We have to split, move some stuff out, move some stuff up to make room for new items. Continue insert of 40. This 40 and 45 need to move over to the new node. This is group C. Move the largest items 40 and 45 out of the full node and into the new node. When the node is full, items need to move to make room for new data. Note, the insert of 40 occurs before the split overflowed the node. This is a key difference between B trees and 2, 3, 4 trees. B trees can move multiple keys. 2, 3, 4 trees could only move one key at a time. That's why it's group C and not item C. Continue the insert of 40. Move key B, the middle 35, up to the parent node. See this 35? It is the middle item of the node we are splitting. It needs to move up. Notice how everybody shifted over to make room for 35. Move key B, the middle 35, out of the full node and into the parent node. When a node is full, items need to move to make room for new data. 50 and 70 in the parent had to be shifted to make a spot for 35. Nodes must be sorted. Keep in mind we are still in the middle of inserting the new item 40. Continue the insert of 40. Leave group A, the smallest half of the items in the full node. Leave them alone. The 33 and the 34, that's group A. Those are the smallest items in the full node. It's not really a step, just leave them be. However, the full node now has room for new data. We're still not done inserting the new item 40. B trees leave multiple keys in the node. 2, 3, 4 trees leave only one key in the node. Continuing the insert of 40. Adjust the child links in the parent node. What does that mean? We need to go up to this parent node, and since 35 moved everybody over, we need to move the links over. Adjust the child links in the parent node. When 70 shifted one spot to make room for 35, the right child of 70 also needs to shift one spot. 70 used to be in this position. It shifted over there. So the right link of 70 also has to shift with it. The right link of 70 shifts over one spot. In fact, every child to the right of 35 has to shift. If you look at the child link between 35 and 50, you can see that it too needs to shift. See this link between 35 and 50? It goes to 55 and 60. That shouldn't be. That link also has to move. And there it moved. We're still adjusting the child links in the parent node. When 50 shifted one spot to make room for 35, the right child of 50 also needs to shift one spot. The old right child of 50 moves over to be the new right child of 50 right there. The child link between 50 and 70 now points to the node with 55 and 60. That's exactly where it should point. Notice also this opens up a child link between 35 and 50. We need this open child link. We're still adjusting the child links in the parent node. Attach the new node to the open child link between 35 and 50. This is good. This is the new node we created because of the split. And the parent between 35 and 50, make sure that you link to this new node. This should always point to the new node that contains 40 and 45. The insert of 40 is now complete. What's the big difference between B tree insert and 2, 3, 4 tree? The insert of the new item, then split the node. B trees insert the new item, then split the new node. B tree algorithms are optimized for disk storage. Each node in the B tree is configured to fit one disk sector. Fewer levels means fewer disk reads. Fewer splits means fewer disk writes. B trees delay splits as long as possible. B trees will not split until it absolutely has to. The B tree root only splits when a promotion up exceeds the maximum number of items. B trees do have a domino effect, where a split at the bottom of the tree can split in the middle of the tree, which could split at the top of the tree. Let's look at some key insert/split differences for B trees and 2, 3, 4 trees. B trees insert before the split. You'll add a new item to the node and then split it with a B tree. 2, 3, 4 trees insert after the split. You split a node before the insert occurs. On a B tree, insert into the leaf 90+% of the time. Most of the time you insert into a leaf on a B tree. Insert into the leaf 100% of the time for a 2, 3, 4 tree. B trees move multiple items when splitting a node. 2, 3, 4 trees only move one item to the right when splitting a node. Split going up the tree. B trees split at the bottom and work their way back up the tree, maybe splitting more nodes. 2, 3, 4 trees split going down the tree. On a B tree, the new key determines the items that move. On a 2, 3, 4 tree, the new key has no effect on the items that move. Why are B trees fast? More records per node means fewer levels. Fewer levels means fewer disk reads. A 3-level B tree requires 3 disk reads, and that would be twice as fast as a 6-level tree that requires 6 disk reads per search. B trees try to minimize the number of levels of the tree. The fewer levels you have, the fewer disk reads are needed. There's also a process of elimination. A binary tree, which is order 2, eliminates 50% of the remaining items by deciding to go left or right. A B tree that is order 10 eliminates 90% of the remaining possibilities. What? How does that work? You scan a node of a B tree. You decide one of 10 paths to take. Well, 90% of the other items are down the other path. By selecting one child among 10, you're eliminating 90% of the remaining items in the tree. Items you no longer have to search. To fully understand a B tree split, you're going to have to understand split patterns. In the example below, the new key that was just added to the node is in red, and the middle key, the one we plan to promote, will be placed in green. As we all know, A stays, B moves up, and C moves right during a split. Splitting 3 items is fairly easy. The largest item is C, the 30 here. It has to move to the right. The middle item B gets promoted up, that's the 20. And of course 10, or the smallest item A, stays exactly where it is. What if you had an even number of items like 4? In that case, I'd make group C the smaller group. Since it's moving, move less items. With 4 items to split, the largest item, 40, would be the one that has to move to the right. 30 would then be the middle item that promotes up, and 10 and 20, the smallest items in the group, would stay exactly where they are. What you need to understand is the new item has an effect on who gets promoted. As a small item being inserted, 10 means 30 is the middle item. If I was inserting a large item into this group, that would make 40 the middle item. The item that promotes up is not determined until after you insert the new item. To a group of 5, how would you divide a group of 5 items during a B tree node split? The 2 largest items, 40 and 50, would move to the new node. B, the middle item, would promote up. Now in this case, 30 is the new item, but it is also the middle item. This is a scenario where the new item does not get inserted into the leaf. If the new item is also the middle item of the node, it will go up at least 1 level and insert a level up in the tree. What if we had 6 items to divide? If we have 6 items in the node, I'd place 2 of those items in group C. 2 largest values after the insert, 40 and 50, would move to the new node. That would make 30 the middle item, and 30 would have to promote. I would leave 3 items in group A and leave them alone. What if we had to divide 7 items? If you had to divide 7 items, it's pretty clear math. There needs to be 3 items in group C, 1 item to promote, and 3 items in group A that stays right where it is. So the 3 largest items, 50, 60, and 70, would move to the new node. 40, which is the middle item in this scenario, would have to promote up. And 10, 20, and 30 would stay right where they are in group A. Once again, I would like to point out that the new item determines what the middle item is. With a small new item, 40 would be the middle item. If I had a large new item, 50 would be the middle item. The new item determines who gets promoted up and who moves to the right. Split on the way up. A node below split and promoted 55 up into this node. When inserted into the root, it causes a root to split also. There is a domino effect on B trees. Nodes below split, move items up, which cause another split, which could move an item up, which causes another split. At this point, we're back to the root, and 55 promoted up into the root and is going to cause a root split. Let's look carefully at the split of a B tree root node. The 65 and 75 had to shift right to make room for the promoted 55. So 65 and 75 moved over, and we inserted 55 into the split. Note, the children of 55 looks weird. See these 2 links here? It looks weird because 55 just split below, and the left is less than 55, and the right link is greater than 55. We'll explain this a little later, but basically it's because 55 moved up, and these are the 2 children of 55. Let's perform the B tree root split now. We've inserted the promoted item, 55, into the full node. Split on the way up. Adding a new root and dividing the current tree into 2 balanced halves maintains perfect balance. Let's create a new empty root node. Here is our new root node. Here is the old root node over here. Node splits promote the middle item, in this case B, or 55. We need a new root so we can promote an item from the old root. This will be the parent when the current tree is split into separate trees. Splitting on the way up, all node splits need a sibling node. Create an empty sibling to the right of the full node. Here is our new sibling node. It will be the sibling of our old root, which is currently splitting. Node splits move the largest group C items to the right from the old root to the new sibling node. So I'm going to move the C items from the old root to the new sibling. Splitting on the way up, same as any split, we're going to move the largest keys out of the full node. Move group C, the largest half items, from the old full node into the new sibling node. Moving the largest group C items, 65 and 75, to the right to the new sibling node, let's make room in the old node. Shown in green are the nodes that are moving. 65 and 75 will be leaving this node and moving to the new sibling. When there are even number of items to split, it makes more sense that group C would have 1 less item than group A. I'd rather move 2 items and leave 3 than move 3 items and leave 2. It just makes sense. Splitting on the way up. You can see the old root node dividing itself among 3 nodes. Move key B, the middle 55, up to the new root. 55 is green to show that it's leaving and moving up to the new root. Move the middle item B, 55, up to the new root node. This makes more room in the old full node. Note 55 was the key promoted up that caused the root split and now is moving up again. 90+% of the time, new keys are inserted at the leaf level. But when a new key is the middle item, it is promoted up a level. So 55 might have started down here at the leaf, got promoted up, caused another split, got promoted up again, and becomes the new root. You can see the new 3-level tree forming. Let's continue the root split. Leave group A, the small half of the items, in the old root. Leave the smallest group A items, 25, 35, and 45, where they are in the formerly full node. Notice how a single node with 25, 35, 45, 55, 65, and 75 split itself across 3 nodes. This is a root split. 2 of the items moved here, 1 of the items moved there, and 3 stayed. I divided the full node among these 3 nodes. Let's connect the new root. Adjust the child links in the new root. Connect the new root to its left and right child. The left child will always be to the old root. Everything less than item B is to the left of B, so adjust the left link of 55 to point to the old root. The right child will always be the new sibling. Everything greater than item B is on the right of B. Now look, 55 points to a node with 65 and 75. Those items are greater than 55. Move the right child to 75. Here's where it gets a little tricky. We need to move child links from the old root to the new sibling. What are we talking about here? When 75 was in the old root, it had a right child. 75 used to sit right here with a right child. We need to take 75's right child from that node over to the new node. Makes sense to me. Moving the child links to the old root to the new sibling. When this 65 was sitting right here, it had a right child. When 65 moves to the new sibling node, the right child needs to move with 65 to the new sibling node. The red arrow shows the old right child. This is the old right child moving to become the new right child of 65. This clearly also becomes the left child of 75. Still moving the child links from the old root to the new sibling. Remember, promotion of 55 from a split below caused this root split. The 55 came from a node that had just split. When the node below split, one node becomes 2 nodes. The new sibling, group C, greater than 55, is now the left child of 65 in the node. The red arrow shows the child references being moved. The former right child of 55 needs to move over and become the left child of 65. This is 55 split's new sibling. We're still adjusting the child links. Because 55 was promoted from below, we've got to be careful how we do this. The 55 came from a node that had just split. When the node below it splits, one node becomes 2 nodes. The old node, which contained group A, those values less than 55, is now the right child of 45 in the old root node. Make sure this points to 55's group A. The red arrow shows the child references being attached. The B tree root split is complete. We have successfully added a new level and root to the tree. If this was a balanced 4-level B tree before the split, it is now a balanced 5-level B tree. It will now take 5 dissector reads to search through the leaf nodes. B trees are designed for disk drives. Each node is a sector on the disk drive. 2, 3, 4 trees are a RAM data structure. It may be helpful to go back and review 2, 3, 4 splits. I find them a little easier, and understanding them gets you 90% towards understanding B tree splits. B trees run at order of log n speed, extremely important when you need to store data in a sorted order on disk drive. Thank you and good night.
Gamesci.com